Hello everyone, I'm Greg Stitt from the University of Florida. I lead the ARC Research Lab in the Department of Electrical and Computer Engineering. And in this talk, I'll be giving you an overview of the Intel Platform Acceleration Card, or the PAC. This is the first video in a series of training modules that will explain how to design applications for the PAC using the Intel Dev Cloud. All right, so what is this Intel Platform Acceleration Card? It's basically a PCI Express accelerator card that provides a field programmable gate array, or an FPGA. There's currently two versions of this card. There's one with an ARIA 10 FPGA. The ARIA 10 is kind of Intel's mid-range FPGA. And there's one with a Stratix 10, which is the high-end high-performance FPGA. If you're not real familiar with FPGAs, it's probably beyond the scope of this talk to give you a background on what they can be used for, what their advantages are, what their disadvantages are. But their basic use is to create custom hardware to accelerate software. And they tend to be especially effective when dealing with energy-efficient acceleration. So in addition to this FPGA, the PAC also provides onboard DDR4 RAM. And one of the really unique features of this card is that it provides the capability of the FPGA to directly request access to a host processor's main memory. In addition, it provides a bunch of other features. For example, it has a networking interface for low latency networking, so you can do network processing directly on the FPGA without having to transfer things into the CPU's memory and then do processing there and then copy it back onto the network. It gives you a lot lower latency, which is important for a variety of different application domains. So this slide here gives you a general overview of what application domains are currently using the Intel PAC. It's used a lot for networking. I already mentioned that it has these low latency networking advantages. And because of that, it can be used for monitoring or network security or for function virtualization. It can really also be used for any type of streaming analytics, either on a network or really from any data source, usually with some form of machine learning integrated into that. It's commonly used for financial technology. So basically for investing, that's one area where low latency processing is critically important, where nanoseconds are very important. It's also used for banking. It's used for risk management. It's used quite a bit for genomic sequencing because in FPGAs, you can do kind of bit level operations and exploit bit level parallelism, which is kind of unique to that application domain. It's used for video transcoding and just general media processing. Very frequently for machine learning. That's not really one application domain. Machine learning applies to probably all of these domains, but it is used quite frequently for machine learning. And really, it can be used anywhere where there is a significant amount of parallelism, because that's really where FPGAs get their advantage, is when you can create a highly parallel circuit. And if you want to look at some specific examples, real-world examples where the PAC has been used, you can look at the Intel FPGA Acceleration Hub, and you'll see some case studies and white papers on actual applications that have used this card. So one really common question is, how do FPGAs and how does the Intel PAC compare to other accelerators such as GPUs? And that's a really hard question to answer because it is highly dependent on the specific application. There are applications where FPGAs can outperform GPUs, and there's plenty of applications where GPUs will outperform FPGAs. So what I'll do on this slide is try to give you just the general trends to get a kind of just a basic understanding of where one might be appropriate over another. So first of all, GPUs, at least the high-end GPUs, have higher peak computational throughput than the highest-end FPGAs. If you look at the current high-end, at least consumer GPUs, you see anywhere from 10 to 20 teraflops. If you're talking about AI performance, it can be over 100 teraflops, but for kind of more general computing, you see 10 to 20. Whereas the highest end FPGAs, I believe, are just below 10 teraflops. So in terms of peak performance, GPUs outperform FPGAs. But the reality is GPUs aren't always able to achieve this peak performance. There's a lot of applications where you don't get anywhere near the full utilization of a GPU. And if you can get a better utilization on an FPGA, then the FPGA might get better performance. Certainly not always, but that's when an FPGA outperforms a GPU, that is why. So another trend that's generally true is that FPGAs tend to be lower power than GPUs, at least in the high-end realm. So the high-end FPGAs consume on the order of tens of watts, whereas the high-end GPUs are 100 to 200 watts. So basically an order of magnitude lower power consumption. And this gives the FPGAs a lot of advantages, especially in terms of energy efficiency. They're not always more energy efficient, but when they are used, they are often used because of their energy efficiency. Because this is important in a lot of different domains. So any kind of large-scale system, whether it's a data center or a supercomputer, these types of systems have enormous power and cooling costs that's on the order of millions of dollars per year, at least. And if you can reduce that energy by a considerable amount, you're making it much more practical to run those types of systems. FPGAs are also very commonly used in embedded systems. The example I have here on the slide doesn't really apply to the Intel PAC because here I'm talking about, so FPGAs can provide what's called system-on-a-chip solutions, where basically your entire system is just the FPGA itself. This is very attractive for applications that need what's called low swap or size, weight, and power. So small, low power, battery operated embedded systems, FPGAs have a significant advantage in that type of use case. And then another point at the bottom is that FPGAs tend to be much more difficult to program than GPUs. I doubt there is a single person in the FPGA community that would disagree with me on that point. And one of the goals of this set of training modules is to try to improve that a little bit. So the most common way of using the Intel PAC is to have software that's running on some host processor, and then a custom hardware accelerator running in the FPGA on the PCI Express card, on the PAC. And Intel refers to this custom hardware as an acceleration functional unit, or an AFU. So this figure kind of shows the basic idea of how that works. So typically the host processor will be executing some software that uses this OPE API, or the Open Programmable Acceleration Engine. And what this does is it handles communication between software and the FPGA. It basically hides all of the low-level details of PCI Express transfers and provides a more abstract API so that the processor can communicate with the AFU. Similarly, on the FPGA side, the AFU is executing kind of the accelerated function, but the AFU designer doesn't want to have to deal with integrating with PCI Express and other interfaces directly. So Intel provides this FPGA Interface Manager, or the FIM. This is basically some extra logic in the FPGA sitting next to the AFU that provides the low-level interfacing details for PCI Express and for various other interfaces, and it provides a more abstract, easy-to-use interface to the AFU. So this slide here just takes a closer look at this FPGA Interface Manager. It essentially provides three interfaces for the AFU. The first one is an interface to the host processor over PCI Express. Now, this interface provides several different communication mechanisms. One is that it gives the FPGA access to the host processor's memory. So basically, the FPGA can initiate transfers to the main memory of the processor, which is a very unique, very powerful capability. Another communication mechanism is memory mapped I/O, where basically the executing software can use memory mapped I/O to read and write to resources inside the FPGA. Both of these communication mechanisms use what's called CCIP, or the Core Cache Interface Protocol. And I'm going to be doing a follow-up video that explains how to use that protocol. The other interface, or one of the other interfaces that are provided, is this external memory interface, or the EMIF. This is an interface that provides the AFU with access to this external onboard DDR4 RAM. And then finally, there's this HSSI, or high-speed serial interface, that can potentially be used for anything, but on the PAC, it provides a high-speed networking interface to the FPGA. All right, so really the main point of these training modules is to explain how to design these AFUs so that you can take advantage of the Intel PAC. And Intel provides several different design entry methods for doing this. The first is what's called register transfer level code. The basic idea here is that you would use hardware description languages such as Verilog, System Verilog, or VHDL to specify very low-level hardware details of the accelerator inside the FPGA or of the AFU. Now, this has various trade-offs associated with it. So if you're writing RTL code, it's very flexible because you can specify the exact characteristics of the custom hardware, which tends to give you very high performance and high efficiency. But the trade-off is that it's also very difficult to do. Writing RTL code is a lot harder than writing higher level code. And as a result, you're probably going to get much lower productivity than you would using a higher level form of design entry. So moving up kind of one level of abstraction, Intel provides several different high-level code design entry methods. The idea here is just to use higher level languages that are similar to C, things that software developers are already used to coding in, that abstract away the details of low-level hardware. So the trade-offs here are that you're going to get a lot higher productivity, at least in most cases, compared to RTL code. But because higher level code isn't as flexible in terms of specifying the exact characteristics of hardware, there's going to be situations where you're going to get lower performance than you would get if you had written RTL code. That's certainly not always the case. There are situations where high-level code combined with high-level synthesis can obtain comparable performance to RTL code, but there are plenty of situations where that is not true. So I have a few examples of these high-level code approaches listed here in the middle of the slide. So OpenCL is kind of a common example of this. So this goes beyond just FPGAs. Kind of the main vision of OpenCL was to create this open language for writing parallel code that can be compiled onto heterogeneous platforms. So not just FPGAs, but GPUs, FPGAs, multi-core processors, really any kind of heterogeneous system. DPC++ is conceptually similar. So this is basically a data parallel C++ language that provides data parallel constructs that give you efficient and effective ways of compiling code onto different types of accelerators. And then finally, another way of designing AFUs, not really designing, but taking advantage of AFUs, is to use accelerator specialized libraries. So the basic idea here is Intel provides libraries of pre-implemented functions that can execute on different types of accelerators. So the big advantage here is that these functions in this library have been highly optimized for different types of accelerators, and they're very easy to use because you just call a function like you would in any other language, and behind the scenes, it gets mapped onto a super efficient implementation on whatever accelerators you have available. Now, the obvious disadvantage is if the library doesn't provide you with functionality that you need, then you have to rely on one of the other design entry methods. So I have a few examples listed here. One is Intel's One API. So the idea here is to kind of hide all of the details of the platform, at least as much as possible. So you basically, as an application designer, you're just concerned with calling functions from libraries. You don't have to worry about, okay, what types of accelerators do I have in the system? How many accelerators do I have in the system? How do I optimize my code for each accelerator? You just call functions, and One API tries to handle all of that optimization behind the scenes using these existing pre-optimized implementations of these different functions. Another example would be OpenVINO. So this is a machine learning specialized toolkit for emulating human vision using convolutional neural nets. So it basically provides highly optimized CNNs for different types of accelerators, and then gives you a toolkit for integrating those into kind of human vision type applications. So as I mentioned earlier, this is really the intro to a series of presentations that will explain how to develop applications for the Intel PAC. I will do this in the context of the Intel Dev Cloud. You can follow along with these training modules if you have the local resources available, but I will be creating videos that show you how to do this on the Dev Cloud. If you're not familiar with the Dev Cloud, it's basically a cloud of Intel hardware that provides you with development nodes that give you access to all the FPGA tools you need to design AFUs. And it also gives you PAC nodes that actually have these cards in them so that you can evaluate the performance and test it and integrate it with applications and things like that. So I encourage you to follow up with those other videos, and there will also be a GitHub repository that provides all the code that I use in the examples that will follow up this video. Thank you for watching.